Okay, our next problem statement. You are watching people practicing archery when you wonder how fast an arrow is shot from a bow. With a flash of insight, you remember your physics and see how you can easily determine what you want to know by a simple measurement. You ask one of the archers to pull back her bowstring as far as possible and shoot an arrow horizontally. The arrow strikes the ground at an angle of 86 degrees from the vertical at 100 feet from the archer. Okay, so first we want to focus the problem, and we draw a little picture of what's going on. We have a guy standing there, or someone standing there, drawing an arrow back, shooting it, and when it lands, the arrow is protruding from the ground at an angle of 86 degrees with respect to the vertical, and we find it's 100 feet from the archer. So the question is, what speed does the arrow exit the bow? Approach. We want to use the fact that 100 feet, the x component of velocity and the y component of velocity determine the angle, so that the angle of the arrow represents the combined angle of the x and y component of velocity. Alright, let's describe the physics. So we have an object with some initial velocity, vix, and some initial y velocity, viy, which is equal to 0. And we also have at tf, the final time, that it now has gained a vertical velocity, vfy, and maintains the horizontal velocity, vix, and at final position, xf equal 100 feet. What is our target quantity? Well, it's vix. We want to know what initial velocity it's exiting the bow, or what the initial velocity of the object is. We don't have to decide what it is by the time we get to this point. What are the quantitative relationships we have involved? Well, we know that the average velocity, vix, is also the instantaneous velocity that doesn't change. So we can write that down as the ratio of the change in position to the ratio of the change in time. We also know that vfy, the final velocity in y direction, is governed by the acceleration due to the force of gravity, g, and that same change in time, tf minus t1. And we also know that we can obtain the tangent of the theta, tangent of the angle, by knowing the components of the velocity. That is the ratio of the final y velocity to the final x velocity, or initial x velocity, which is the same. Okay, let's plan the solution, and let's start with an equation that has the target quantity. And we can start over here, of course, with the initial velocity in x direction of the object over the ratio of the change in position to the change in time. But we don't know what this change in time is, so can we substitute? Well, we have another relationship. We have the relationship that the final velocity in the y direction is equal to minus the acceleration due to the force of gravity times the change in time. We can solve for that change in time, and what we want to do is substitute for that change in time. We now come out with a relationship between the initial velocity in the x direction, the final velocity in the y direction, gravitation, or the acceleration of gravity due to force, and the change in position. We also go back to our relationship of tangent theta, because right now we have two unknowns in this equation, so we have to have another relationship. So we can solve for vfy in terms of vix and tangent theta, substitute, and with a little bit of algebra, we come out with that the initial velocity in the x direction is equal to minus the acceleration of gravity times the change in position over tangent theta of all quantity to the 1/2 power, or the square root. Okay, let's substitute and execute the plan. Beginning with our equation, we'll just substitute numbers. So it's 100 minus 0 times minus 32 feet per second squared, the acceleration due to the force of gravity, over tangent to the minus 4. And that's 214 feet per second. In evaluating the solution, we asked several questions. One of them is the answer properly stated? Yes, it only asks for the initial velocity, which we have given. Is it reasonable? Is it unreasonable? No, it's not unreasonable. It reaches 100 feet in about half a second, which we would consider to be reasonable time. And is the answer complete? Yes, no other information is asked for.